Oh, come on. Okay, welcome. Today is our notes on gravitational field and a review of the two concepts of mass and weight in here. Now first of all, let's go back over to mass here. Remember, mass is the amount of matter that something is in. This is the amount of matter in a substance. It's measured in the units of a kilogram, and it does not depend on your location. You do not change your mass just because you move from one place to another. Your mass will be the same on the Earth as it is on the Moon, as it is on Jupiter, any other place that you go. Weight, though, is a whole different ballgame. Weight is equivalent to the force of gravity. So weight and force of gravity is exactly the same thing. And the force of gravity is a combination of an object's mass multiplied by the acceleration of gravity, the value for g. Now, near the Earth's surface, g is 9.81. But if you go higher up, it becomes less. If you go to the Moon, it becomes less. If you go to Jupiter, it becomes more. So your weight depends on location. It will change depending on where you go. That is, different places in our universe, you'll have different weight. The units for weight is the force unit, which is a Newton. And of course, the Newton is abbreviated with a capital N. Mass is measured in kilograms. Weight, or force of gravity, is measured in newtons. What really bothered scientists was this whole idea of how something like a ball, an apple, the Moon, could actually interact with the Earth. I mean, it's easy to see that if you apply a force to a ball, you can throw that ball across the room. Not so easy to see if you take an object like a ball or a rock or something and you put it above the Earth. How does that object in fact move downwards toward the Earth? How does this object up here know that there's an Earth here and it should move down towards it? Well, this answer that scientists came up with is something called a gravitational force field. This force field completely surrounds the Earth, and it directs anything near the Earth to move around what's called the gravitational field lines. Now, an object that is really, really close to the Earth will experience a high acceleration towards the Earth. An object that is further away will experience less of that acceleration. The gravitational force field is stronger close to the Earth, weaker as it moves further away from the Earth. The strength of the gravitational force field, called the gravitational field strength, believe it or not, is equivalent to the acceleration of gravity. So the gravitational field strength, G, F, S, is equal to the acceleration of gravity, G, at that particular location. That's amazing. So, near the Earth's surface, the gravitational field strength, as you know, has a value of around 9.81 meters per second squared. Now, the unit that we use for gravitational field strength is a Newton per Coulomb. Newtons per kilogram, not Coulomb. Newtons per kilogram and meters per second squared are identical units. They're exactly the same. You see the units that into here. All right? Now, how do we come to number 9.81? Well, number way, we did in class, we measured it, we come up with the value onto here. I want you to take a look at this here. This is the latitude. Remember, latitude from an Earth position is the distance measured away from the equator. So if this is the Earth, you imagine me drawing an Earth in here like this. There it goes, a bit of a circle in there. There's the Earth in there. And you imagine the line that runs straight from the center of the Earth in there. We call that line the equator. The lines of latitude are lines, of course, that run in circular nature, parallel lines that run both in the north and in the south direction as they go around the Earth like this. Okay, so this is 0. And as you work on your way up, you're going to get 10, 20, 30, 40. The very highest point up here, you're 90 north. And the same thing happens down below. You're 90 degrees south and 90 degrees north in here. Lines of latitude that's on here. So if you look at this, as we go further north, so as we walk, if you like, from the equator towards the North Pole, the values for G get larger. Now, why is that? Well, if you look at that, look at the distance here. At the equator, you have a distance of 6,378 kilometers from the Earth's center all the way to the equator in there, radius of the Earth. But the same distance as measured to the North Pole is only 6,357 kilometers. That's this distance right in here. So the distance to the equator is greater than the distance to the North Pole, which means, of course, that you're further away at the equator than you are at the North Pole. The further away you are, the weaker the acceleration of gravity, hence 9.78 the equator, 9.832. Therefore, you will weigh more at the North Pole than you will weigh at the equator. All right, makes sense? The value here, 9.81, if you take all these values here and average them out, you will get 9.81. That's the average value. And it's also, if we look where we are, about 49 degrees, pretty close to that value there, and so that's why we use it 9.81 in the classroom. Now, the acceleration of gravity also depends on your height above the Earth as well. So again, if you imagine, this is the Earth in here. If you're at the Earth's surface, you're going to have 1 G value. If you climb to the top of the mountain, because you're further away, you're going to have a less force of gravity. If you dig a hole to the bottom of it, the closer you are to the Earth center, and here, the greater your force is. So at this up here, your weight or force of gravity will be one value. It'll be greater if you are closer to the Earth's center onto here. Further away, it's less. Closer to the center, it's greater into here. And that's what these numbers here indicate onto here. But for our purpose, 9.81 will be the acceleration of gravity or the gravitational field strength of the Earth. And it measures how strong objects are pulled to the Earth together. And the gravitational field is how the force between the Earth and some object interacts, allowing objects to fall down towards the Earth.